My name is Chad Mason, and welcome to Lecture 9. Today I'll be presenting on tool steels with an emphasis on H13. So just like I said, material is H13. Its significant properties that dictate material use are it maintains toughness and hardness at high temperatures, which is why the typical applications are in injection molding dies and shear blades. So some of the material properties, I actually got this straight off of Brenton's paper that he sent me. I thought it's a really good overview, has a ton of information on it. If you look, it has AM averages, and it also has the range, and then it compares it with the wrought material. So if you look at the hardness, it's actually just about where the wrought material is. Obviously the wrought material has a really large range, so it's pretty easy to get in there. But the theoretical density is kind of where the AM comes into play, especially with H13. You can get very close. There's going to be a few different processing techniques that will get you higher theoretical densities, which we'll talk about that later. So he actually got all this information from all those sources that are that says table 9, and it says that. So basically he did all the work and formed this table, and that's why I chose to use it. So as far as vendor, I believe it's Carpenter. They're in Pittsburgh. They didn't really say a whole lot about their powder and material. I went on their website. They have all sorts of materials, and I just searched it and found it, so that was pretty nice. But AISI type H13. I believe AISI is just as far as a case study, I couldn't really find anything that had what I would think of as a useful part that has that they would actually talk about and say like how much time and stuff it took. But what I did include is a picture of an experiment using LC process. I have a photo right there on the left that shows what the LC process really is. Then on the right they're just building up little square tubing. As far as my research study, like I said, got a ton of information from Brenton. So this is from his unpublished paper. As far as what I'm looking into, or what he's looking into, is he's pulling information from about 4 different sources to understand if energy density correlates to the percent theoretical density. What does that mean? Well, the important takeaway is SLM has a clear correlation between increased energy density and improved theoretical density. So the blue data points are SLM, and then the red ones are DMLD, and I don't know what the 43 and the 15 are. Basically, SLM has a pretty large spread, and so that's why it correlates between the increased energy density. And also the SLM, you can get the theoretical density about 98%. And then DMLD, you can get really close to 100. The next research study, so the experimental description is just pulling information, this time from 9 different sources, to understand if particle size affects the theoretical density. So this is an unfinished table that has kind of a good representation that can show you that the median particle size of 100 micron or 150 micron shows the highest theoretical density. There's my references.